So I will talk about behavioral mainly, and only if I have time also about brain processing of different types of questions. So first, let me start by explaining to those of you who are not familiar with number processing that there is a convention now that when we see a number, when we hear a number, we have a feeling of how much is it. And this is true for whole numbers, but my study is what about fractions or rational numbers. So let me just show you how whole numbers are being studied. How is this conclusion came? So automatic processing of numerical meaning was tested with physical comparison tests. So we see here two numbers, and they differ in their physical size, the font size. So if I ask you which number is written in a larger font, in this case this is quite simple, it's the 4, and here, I'm not testing you, so here it's the 3. And the difference between these two conditions is that the first one that I showed you, the 4 was larger, and 4 is also numerically larger, so this is a congruent trial. And the second pair, where the 3 is physically larger, it's an incongruent trial because 3 is numerically smaller. And Henrik and Zettel in 1982 showed that reaction times for the incongruent trials are slower than for congruent trials, and this is called the size congruency effect, and it shows that even if we try, we cannot ignore the meaning of the numbers. The numerical meaning is automatically processed. So as I said, my question is what happened with rational numbers, and the rational numbers will have different kind of them, so just to make sure what I am talking about. First, non-symbolic rational numbers can be presented as ratios, as proportions, as part of the whole, and symbolic notations of these non-symbolic entities can be fractions, decimals, percentages, and ratios. Today I will start by presenting a study about fractions, and as I said, only if I have time I will continue to the fMRI, study to the brain part, that was supposed to be, which will be about ratios. In both cases, there will be the symbolic notation. So just to make sure that these two notations, the fractional notation and the ratio notations, are distinguished, although it looks very similar, it has a little different meaning. So, for example, a ratio of 2 to 3 means that we have 2 of one kind and 3 of another kind, and the fraction 2/3 are 2 out of 3. So, of course, there's connections between them, but also a difference, just to make sure that this is it. So, I'm starting with fractions. And what do we know about the representation, processing of fractions so far? A lot of works, including my own, show that the components of a fraction, the digit components, which are the numerator and the denominator, are processed automatically, but the fractional value itself is not. Me and Zhu call this the whole number bias, although they didn't really talk about the automatic processing, but as a whole about the strategies that children use when they try to solve problems with fractions. But I think it also fits very well my question about the representation, the automatic processing of fractions. So, for example, when we see a pair of fractions, like here, we have 2/5 and 3/4, what participants or people automatically process is the 2 and the 5 and the 3 and the 4, but they don't automatically process 2/5 and not the 3/4. On the other hand, I showed that if we compare fractions to whole numbers, then we do see that participants automatically process fractions as smaller than 1, no matter what the components of the fractions are. And I will show you how I measured this, how I did it. So the evidence for the automatic processing of the fractional components were found when I showed participants two boxes with fractions in them, and I told them, ignore the content, just tell me which box is larger. And then this, for example, should be an incongruent, right? Because half is larger than fourth, but half is in the smaller box. So this should be an incongruent, right? But what I showed is that it is processed faster than the congruent trial, which is fourth in a smaller box and half in a larger box. So, of course, you can see in this case that 4, which is the denominator, is larger than 2. So what I conclude from these results is that participants were actually processing only the denominator in this case, the components. In the case of the comparison of fractions to whole numbers is where I use the same boxes, but in this case I put a whole number in one of them and a fraction in the other. And then I show that no matter what are the components of the fractions, they were always processed as smaller than whole numbers. And I call this a generalized fraction, that the structure of the fraction is being processed as something small. And here are common results that I get. This is from my PhD thesis. So if I compare two integers to whole numbers, then we get the regular size congruity effect. Congruent is faster than incongruent. But if I show two fractions, then we get the first effect. And if I show a mixed pair of a fraction and a whole number, then no matter what were the components of the fraction, the size congruity effect was correct, was in the right direction. So, of course, fraction can be processed intentionally if needed, and this was shown. And I'm talking here, maybe I should have said this earlier, but most of my studies are with students, adults, not with children, because I'm looking for what exists after they finish their learning phase. And if needed, adults can calculate the value of a fraction. But I'm interested in the representation, the mental representation, and my question is whether, besides just calculating the value of a fraction, do we also have a representation of a unique entity for fraction, at least for more common fractions, for more familiar fractions? And this question is about whether we are processing fractions holistically being as one entity, as an integrated entity. The problem is that if I ask participants to intentionally process fractions, then of course they can do it, but maybe they just have efficient strategies. And if I use the automatic processing, the task that I just showed you, then as I just mentioned, we have a very strong activation of the components, and it doesn't necessarily means that we don't have in addition also a representation for the fractional values, because the components are the digits are being used in everyday life much more often as whole numbers, and maybe the representation of the whole numbers is just stronger, but somewhere in the back we also have maybe a representation of a weaker representation of the fraction. So this is a problem. And for this, the study I'm going to show you now uses improper fractions, and I'll explain you why I think this is a proper way to look for holistic representation of fractions. So first, when we introduce fractions in elementary school, we use the horizontal line, so the numerator, then horizontal line, then the denominator below it. On the other hand, when we teach division, also in elementary school, then we use the colon, and I know that in English-speaking countries there is other symbol that I don't know how it's called. So let's say the colon. But later on, high school, in college, and also when people start to use computers and they write down in one line the fractions, they use the slash both for fractions and for division. So this notation with the slash, with the diagonal line, is used both for fractions and for division. And what I thought is that it might elicit a division schema for fractions. Now, I'm not alone here. I'm collaborating on this study with David Gomez and Pablo Darnell from the University of Chile. And we hypothesized that a division schema like this would be activated more often in the case of improper fractions. First, because in this case, it resembles the familiar situation of division, where the larger number is divided by the smaller number. And also because in improper fractions, the part of the whole schema is harder to apply. So the stimuli in this study were non-unit irreducible fractions. We had 2x2 conditions that following study by Gomez et al. With and without common components, and also congruent and incongruent conditions between the fractional value and the component value. So I will just show an example here. So the top left box is congruent pair with common component, which means that if A divided by B is larger than C divided by D, then A is larger than C and B is equal to B. B here is the common denominator. And since I'm short of time, then I will let you fill up the rest of the conditions. The improper fractions were created by inversing proper fractions. And as I said, I used the diagonal fraction line to encourage the division schema. So here are examples of the stimuli. We had 6 pairs in each category, but I'm showing you just 2 examples from each category here. So for proper fractions, and this is the improper fraction, I just want to note how we inverse the fractions. So for example, if proper fractions, we had an incongruent pair with common components, so it's 3 divided by 13 versus 3 divided by 8, so this is a common numerator pair, then the improper fraction would be 13 divided by 3, 8 divided by 3, and here is another example. Hopefully this is clear. The hypotheses were that if the processing is only componential, then there shouldn't be any difference between improper and proper fractions because there are the same components in both conditions. But if some degree of holistic processing exists, then maybe it's a question, we will get a difference between proper and improper fractions. And then if this difference will be in the direction that we think it will be, then it might suggest that some holistic processing exists after all, even when the components are processed more strongly. We had 2 tasks, the intentional comparison task, where we were just asked to say which fraction, or actually we didn't say the word fraction, we said numerical entity because we didn't want to direct them to think about it as fraction. So which numerical entity is numerically larger, and the automatic comparison task where we ask them to just say which numerical entity is written in a larger font size. I'll start with the intentional task, although it's not the most important one for my purposes. But here what we see is participants use strategies and not always the good strategies. So first let me walk you through this graph. So what we have on the x-axis is the improper and proper fractions, and then with common and non-common components, and the bars are gray for congruent and black for incongruent. And I remind you that here congruent and incongruent means congruency between fractional value and the components value. And what we see is that first, common components lead to faster reaction times and less errors. And if the interesting thing is that if you look at the error rate, then you can see that if the common component, if the trial was congruent should be actually easier. Participants did more had more errors, and this is probably because they were using a bad strategy, which was based only on the denominator. So the larger the denominator, the smaller is the fraction, and because they used only the denominators, they were wrong actually in the congruent trials. So what we get from this task is just that participants are not good at choosing their strategies. But I'm interested more in the results of the automatic task, because this is where I'm looking beyond the strategies that participants are using. And here, first, again, this is a complex graph, so let me again show you what we see here. So here on the x-axis, we have common versus non-common, and then the congruent versus incongruent, which is the same congruent and incongruent as the last slide, congruity between fractional value and components. The gray bars are the improper fractions and the black bars are the proper fractions, and most importantly, here the y-axis, this is not reaction time, this is actually the size congruity effect. So if it's positive, it means that size incongruent trials will process slower than size congruent trials, which is which is what we are expecting. And what we can see here is first that components are being processed automatically, which is not surprising. This is something that I found before. And we can see when we compare, for example, a congruent and incongruent trials. So we can see that whenever the components are incongruent with the fractional value, then we get a negative size congruity effect. We also see that the effects are larger, both to the negative and to the positive sides. They are larger when there is no common component, because they are just two numbers that are going to the same direction, so this is also expected. The interesting comparison here is between proper and improper fractions. And if you look at it, you can see that whenever the size congruity effect is positive, then the effect is larger for improper fractions. And whenever the size congruity effect is negative, then the effect is actually smaller for the improper fractions. Which I conclude from this is that there is something else that is being processed and is pulling the results, the effects, to the correct direction, to the correct size of the size congruity effect, the positive side in this case, which is, I think at least, is the processing of the fractional value of the, in this case, probably only the improper fraction. So I will conclude this study, and as I thought I don't have time for the second one. Improper fractions show larger extent of holistic processing. This sentence is not completed, so I apologize. If the division schema is responsible for this effect, then it may indicate that introducing fraction as division would be more efficient, would be better to explain fractions to children. What we see here in this case is not only for children, also adults that are already finished their education, their education can benefit from it. Of course, following my discussion with Ron last night, this should be following a proper introduction of division and multiplication. And my future plan for this specific study is to also test a similar design, but with the horizontal fractions used as we learned them in elementary school, just to make sure if what I got is based just on this specific notation, or is it improper fractions in general. I'll stop here. Thank you.
We have time for one question, if you may. is always more positive or less negative than for the proper.
Exactly.
Okay, so it's not really going in different directions. It's going in the same direction, but it's in a different place.
Right, it's going to the same direction when the components are going to the same direction. Also, have positive effect, but it's going to a different direction when the components suggest the different direction. So this is why it's more positive when it's positive, and it's less negative when the negative, what we see here from the negative size-control effect is a result of the components, because larger components in these cases were in the smaller fraction. So this is why it's, in these cases it's going to the other direction. But yes, of course, this is what I thought I was saying, that when the components and the fractions are going to the same direction, then it's in the same direction, but otherwise it's opposite directions. Did I answer your question?
I deeply apologize, but we are really out of time. So, yeah, I apologize. So, thank you, Arava, again, and I'm very happy